so today we're going to talk about a couple more properties, one of them being electron affinity. So this is actually an energy change whenever an electron is acquired by a neutral atom. What we see is that this tends to increase across a period. Have you guys heard of affinity before? Like you have an affinity towards something. You have an affinity toward dogs, or you have an affinity towards cooking. Yeah, you're drawn towards it. Yeah, that's a good way to put it. So the affinity specifically is how much the energy that is changed whenever an atom acquires an electron. Remember, the idea is that atoms want to go to the lowest energy state possible. So they're going to lose this energy. So the ones that are more likely to lose this energy would be like my fluorine over here. I want to show you electron affinity on a scale. Notice, whoops. Notice that the darker purple ones over here with fluorine. However, my noble gases, they're all actually at 0. So you just want to be aware of that the noble gases don't have an electron affinity. They don't want to gain electrons. On the other hand, fluorine does. Some of the lower ones you see down here, like francium, cesium, have lower electron affinities. Because in general, I know it's not perfect, but in general, the electron affinity is going to increase as we go left to right, and it's going to decrease as we go top to bottom. Just like ionization energy did. And they sound the same. Ionization energy, remember, is how much energy it takes to take an electron. Electron affinity is similar, but if you think of it in terms of money, the ionization energy is like, how hard is it to take away the money I already have? It's like I might have it locked up in a safe or something. It's a lot harder to take my money than if it's just, sprawled out everywhere. So the ionization energy is how much energy does it take to take an electron from an atom. Whereas maybe I'm really drawn toward money. I want to make a lot of money. That would be more like the electron affinity. Playing the Powerball numbers, I'm more likely to gain money. I have an attraction towards it. If I win the lottery, that would be kind of like fluorine. Fluorine really just is the best at ending up with electrons. Probably a bad analogy, but hopefully that makes sense. The difference between ionization energy, which is like taking the electrons I already have, and electronegativity, which is gaining new electrons that I don't have. So hopefully you see the trends there for that. Looking at the noble gases, what do you think? Noble gases, do they have high ionization energies, high electron affinities, large atomic radii, or tendency to form ions? Oops. Any ideas there? Yeah, it's high ionization energies because they don't. We see here they have 0 electron affinity. However, we look at ionization energy. That's where we hit the maximum.
Any 10th grader who needs to get their picture retaken but was absent on picture day, come down to the auditorium at this time.
So then this kind of goes along the same lines. Any idea how we would rank these in terms of increasing electron affinity? It had to be one of the ones with krypton at the end, which is all of it. But you mean on which end?
I mean the right end.
So you think krypton has the highest electron affinity?
No, electron. Okay.
There you go. Yeah, so this one would be D. Good job.
I was thinking increasing whichever one.
The ionization. Gotcha. That's fair. All right, so now we're going to talk about ions a little bit. There's two types of ions. There's cations and there's anions. Cations are the positive ones, and the anions are the negative ones. I don't know if I'm thinking that the N in anion might help remember that, but cations, if you don't like cats, it might be harder to remember that positive goes with cat. But one thing you can remember is that the cation tends to be smaller than the original atom. We are losing electrons, we're giving up electrons, so we're actually oftentimes shedding an entire energy level when we become a cation. So that's going to cause the positive ions to become smaller. In addition, the remaining electrons are drawn closer to the nucleus because there's an unbalanced positive charge there. With anions, because we're gaining an electron, we're filling our outer shell. This always actually increases the size of the atom. So anions are always bigger than the original atom. So how do these trend? Just like size did, these things are going to increase and decrease across the period. We looked at this picture. Not this one. It was this one here. Just like atomic radius decreased as we went from left to right, you're going to see the same thing with cations and anions. They're going to decrease as we go from left to right. Ions are also going to increase as we go top to bottom because just like the atomic radius, we're seeing an addition of shells. So we're going to see that addition of that increase in size. So with my ionic radii, the outer electrons and cations and anions are in higher energy levels, so you see that increase that I mentioned. Now talking about the outer energy levels, we have a name, a special name for electrons that are in those outer energy levels. They're called valence electrons. Those would be electrons that are lost, gained, or shared in reactions or bonding. And they're often located in incompletely filled main energy levels. My example here, we talked about sodium, the cation sodium. When we look at sodium on the periodic table, remember it is going to be filling that 3s1 orbital. So that highest energy level, that's its valence electron. And I just want to point out, it has one valence electron. It's in group 1. Magnesium would have 2 valence electrons, as would any element in group 2. Aluminum has 3. Silicon has 4. Phosphorus has 5. So in this, the P block, the number of valence electrons just depends on the group number minus 10. So this group has 3 valence electrons. See, in this case, 2 is my highest energy level. So I've got 3 electrons in the 2 energy level. Gallium might be a little tricky because I have 4s and then 3d and then 4p. But valence electrons we're only worried about the highest energy level. So this 3d row doesn't really count. We're just looking at the valence electrons in the 4s and the 4p. So gallium has 3, indium has 3. Everything in group 13 has 3 valence electrons. Group 14 we have 4, 15 we have 5, 16 6, 17 7, and 18 8. So for the P block, you can just remember valence electron is group minus 10. In the S block, it's just the group number. So I just want to talk about this question with you guys. Which electron configuration is not correct? If we look at the charge for oxygen, it's got a minus 2 charge. Since electrons carry a negative charge, that means I have added 2 electrons. So the normal electron configuration for oxygen would be helium 2s2 2p4. We look at oxygen, helium 2s2 2p4. So when it gains those 2 electrons, it becomes helium 2s2 2p6. Does that make sense? How it gains the 2 electrons. So this is correct. Magnesium with a 2 plus, because the electrons are negative, that means the nucleus is winning that battle of charge. So the nucleus has more charge than the electrons. So that magnesium has lost 2 electrons. And I go from being, magnesium is normally neon 3s2, but I lose those 2 electrons. So I go back to being like neon, which is 2s2 2p6. Does that make sense? It's going back 2. Now, in letter C here, vanadium, with a 3 plus charge, it's going to lose its 3 valence electrons. So normally it's 3d3, but I lose 3 electrons. So I essentially go back to being like calcium. I'm sorry, I misspoke there. Vanadium, I'm losing 3. So first the electrons are gonna disappear from my 4s orbital. And then I lose those 2. And then I also am going to lose 1 from my 3d orbital. So that one is going to be 3d2. And finally, with my aluminum, I should lose 3. So aluminum, that would take me back to being like neon. The incorrect thing here is that it says argon 2s2 2p6. It should be helium 2s2 2p6. So there's a lot there in that question. Does anybody need me to reiterate anything? You guys are good?
Any 11th grader who needs to get their picture retaken or was absent on picture day, come down to the auditorium at this time.
All right, so looking at the elements that are most likely to have the same charge on their ions, we've got selenium and arsenic, which are side by side, selenium and arsenic. We've got tin and silicon, which they're in the same column, but they're separated by 1. We've got calcium and rubidium. They are kind of catty corner over here, calcium and rubidium. And then we've got iodine and xenon, which are side by side over here. So looking at those pairs, any guesses on which ones will have the same charge on their ions? Yeah, I agree. Because they're why is that logical? Because they're in the same group, same column. So they would have. Remember, we said they have 4 valence electrons, so they're most likely to have the same charge. Elements in the same group are most alike. So there's one last thing we're going to talk about, and that is electronegativity. Very similar in a way to electron affinity. However, electron affinity is specifically talking about the energy that is lost when an electron is gained. Electronegativity is the measure of how much the atom is able to attract an electron. So it's literally almost like a GPA on a 4.0 scale. When we look at our properties here, electronegativity. Can I find it? There it is. So electronegativity. Fluorine has the highest electronegativity, not quite a perfect 4.0, but 3.98 is very high on the 4.0 scale. very low electronegativity is francium, which is 0.7. So you can see the lighter yellow is low electronegativity. The darker gold color is high electronegativity. Fluorine is in fact the highest, the most electronegative element. These noble gases do not really care to gain electrons. You see there are exceptions. Krypton and xenon do have that ability to gain electrons, but for the most part, noble gases do not. And we don't even give them an electronegativity. So just like the electron affinity, just like the ionization energy, electronegativity is going to increase across the period, and it's going to decrease as we go down the group. So looking at my example here, gallium, bromine, calcium. So gallium, bromine, calcium. Which one's got the highest electronegativity? Gallium, bromine, or calcium? Gallium, bromine, calcium. Calcium or bromine. So calcium looks like it's a 1.0 over here. Bromine's at a 2.96. So I think it's going to be bromine, right? Yeah, the darker it is, the more electronegative on that chart. But we also know the trend is that the electronegativity increases from left to right. So again, the key is know that fluorine has the highest electronegativity. It's important in that way. That kind of wraps up the chapter, everything we're going to talk about as far as trends go in valence electrons.